Okay, so we are going to look at some of our rotational motion now in greater detail. I know that our introduction video was quick. I tried to hit all the topics in kind of a brief overview. So now I want to kind of delve into some very specifics about our angular changes and our angular velocities and our angular accelerations. So now we're really going to kind of get into this. And a lot of this is going to parallel the linear sense versus the angular sense. So we're going to see some of those parallels as we go through the video here tonight. All right, so let's get started. If we start to talk about how we measure angles, and now this is the big thing. In a math class, you probably had to spend some time looking at angles, and we looked at things like the unit circle. Okay, so I chose a picture of the unit circle because you probably had to know the differences between, say, 60 degrees, and that 60 degrees was equal to pi over 3 radians. Okay, and that was something that we had to kind of learn in a math class. What is a radian? Okay, radian by definition is a arc length ratio to radius. Okay, so what does that kind of mean? Well, it means that if I look at, say, an angle we always use theta to describe an angle measured in radians is equivalent to the arc length over the radius. Okay, S usually represents arc length. Okay, so S is for the arc length, where R is the radius. Now, arc length is something that's a unit measured in, say, meters, centimeters. Okay, it's a unit of length. And when we take the radius, which is also a unit of length, we end up with a unit of length divided by a unit of length. So really, the angle is something that has no real true unit attached to it. Okay, and that's why we define it then as a radian. Okay, so radian is kind of a unit that we use to describe an angle change. Now, we also look at it in terms of if we completely spin something around. So if I spin something around, I create like a revolutions. Okay, so we always can count number of revolutions. You may know that in your car you have a gauge that actually measures RPMs. That's revolutions per minute. Okay, so that's something that we look at as well as a unit. So we have an equation then that says 1 revolution is equal to 360 degrees or 2 pi radians. Now what that really tells me is that I have an equivalence between both radians and degrees, and that's something that we may have to do. We might have to do a conversion from degrees into radians. We actually have done this already in this class. And if I just kind of look at this as being 180 and this as being pi, okay, there's 180 degrees in pi radians. Okay, so that's a way that we can use that as a conversion factor. Okay, and really it's about measuring those angles, because the change in these angles will give us change in our arc length. So if I increase my angle, I increase my arc length. The radius usually stays the same. Okay, we don't change our radius as we're changing our arc length. Okay, and that's what we're going to kind of get into when we move on into the next part. Okay, so now we're going to change our angle. So again, I have an angle and it's going to change. So I have a changing angle. Well, if I have a changing angle, okay, this has to happen in some given amount of time. And that's really what we're going to kind of look at. So if I look at my change in my angle with respect to time, I have something that I look at and say, oh, well, this should be a value that is a rate of change. Let's define this as something. Well, we're going to define this as, and this is now the Greek letter omega, this is my angular velocity or an angular speed. Okay, so angular speed does this. It describes the rate of rotation. So how fast is that angle changing? How fast is that angle changing? For those of you that are calculus students, you're going to notice that you'll see d theta dt. Okay, so that's just the derivative of a position function, or of a, not of a position function, but of an angle function. So if we can define the angle, that's the derivative of that would be then our angular speed. Okay, so again, average angular speed is just a change in our theta, okay, angular displacement over a set time interval. Okay, so that's easy enough for us to look at. let's take a little quick look at a problem, okay? So how does this play out when we see this on our problem set? Well, here I have a girl. She's got a little toy airplane. She's tied it to a string. She's spinning it around her head, okay? We found out that the average angular speed is 2.2 radians per second, okay? So that's how we figure. How could we have figured that out? Well, maybe we counted the number of revolutions that it took for her to do in a certain amount of time. We said then that's an average, so we then equate that into our radians per second. So we've got our average angular speed. Now the question would be, now we're getting kind of specific here, how long, okay, this is a timepiece, will it take for the plane to move through angular displacement of that many radians, okay? So now I have my omega, okay? Omega is 2.2 radians per second. I'm looking for a time in seconds based upon that I'm going to change my angle 3.3 radians. Okay? So now I'm just going to kind of set up this equation, and again, because it's the average angular speed, okay, and this was average angular speed, I can just set it up to be 2.2 radians per second is equal to 3.3 radians over t seconds. Now I have to do a little bit of algebra, okay, so I have to bring the t over to this side, and that'll give me t times 2.2 radians per second is equal to 3.3 radians. I'm going to divide by 2.2 radians per second, and then I'm going to find out what t is. Okay, so I'm just going to take my 3.3 divided by my 2.2, and I get 1.5. Now the radians parts cancel, and I'm left with then seconds. So it takes 1.5 seconds to complete that task for this girl. Okay? So, angular speed. We'll see some of these problems on the problem set. Now, not only do we have angular speeds, but we could have angular accelerations. Okay, so now how fast are we changing that angular speed? Okay, now again, we're looking at a change in our angular speed in some unit time. Well, that's going to give us an angular acceleration. We use the Greek letter alpha to represent angular acceleration, and again, this is kind of on the average. So the average, it would be the difference between our two divided by that time interval. Okay? So our average acceleration, angular acceleration, is just the change in our angular speeds divided by time. Okay? And so this is typically what we see. We may see like we have a figure skater that's spinning around, and maybe you've experienced this before, but if I pull my hands in, I'm actually changing my angular speed. So I'm going one angular speed here, then when my hands come in, I go at a different angular speed there. Well, that requires me to have angular acceleration. Okay, so I'm going to look at a problem that kind of deals with this. So I've got my figure skater. They begin to spin counterclockwise at an angular speed of this. So that's my starting, or my omega initial. During a 3-second interval, that's my time, she slowly pulls her arms in until she gets to this speed. So that's my omega final. What is the average angular acceleration during this time? So I'm going to take my alpha, and it's just going to be my 8.0 pi radians per second minus my starting, which is my 4.0 pi radians per second. And I'm going to divide this by now 3 seconds. Okay, so if I have 8 pi minus 4 pi, I end up with 4 pi radians per second divided by 3 seconds. Okay, so I'm going to take my 4 times pi times, divided by 3 seconds. So my angular speed acceleration comes out to be 4.19 radians per second squared. Okay, it's radians per second squared, very similar to meters per second squared. So we see that kind of similarity between what we're looking at. Okay, again, similarities between linear versus the angular. Okay, so again, here we go, back to this, looking at the similarities. Linear versus angular. Okay, you're going to see we had a bunch of kinematic relationships for constant acceleration, and these are our 3 formulas that we had on the board over there. Now they're using x's, we used d's. Okay, it's just the graphic that I pulled up, and they have a v naught, but that was just vi, or the initial velocity, so there'd be the same type of thing. Under constant angular acceleration, so again, we're going to have constant angular acceleration, we see similarities. Okay, so you can see the parallels between these equations. They're the exact same thing, just that we're using the Greek letters now. Okay, so I think I've got one more problem that I want to kind of talk about here. So I have my a diver performing a double somersault at an angular speed of 4 pi radians per second. So that's my angular speed. Okay. And precisely at 5 seconds after leaving the platform. Assuming the diver begins with 0 initial angular speed, okay, that means that this is a final, and this is my time. What is the diver's angular acceleration? Okay, so now we're looking for angular acceleration. I have Wi, I have a Wf, and I have a t, and I'm looking for this. Okay, so again, I'm looking at these 1, 2, 3, 4 variables. I'm looking for 2 w's, so I got a ww, and I've got a t. It looks like I'm going to use an equation that looks like this. Okay, so my final was 4.0 pi radians per second. My initial is 0. Plus AT, so alpha, and the time was 0.50 seconds. So now I'm just going to divide by 0.50 seconds, and my angular speed comes out to be 4 times pi divided by 0.5, 25.12 radians per second squared. Okay, so again, we can kind of see how this is all going to take place. Oops, let me back up here. And we can then look at how they parallel. So now on the board, I've got some stuff in purple, and hopefully that'll help you out. Now I got a phone call, so I'm going to kind of quit it right there, and we'll see you in the next video.